Welcome to Lesson 11b, Observations about Stokes Equations. In this lesson we discuss several observations about Stokes equations. We'll mention Stokes Paradox and Odens Improvement. As a quick review, for 3D creeping flows, we have these Stokes equations, continuity and momentum, in vector form. Now let's make some observations. First, we notice that density does not appear in the equations. In the original Navier-Stokes equation, density appears in the inertial term and in the gravity term, both of which we're neglecting here. The result, then, is that pressure and viscous forces depend on viscosity mu, with no dependence on density. Consider, for example, a falling particle from a volcano. A volcano can spew particles way high into the atmosphere, perhaps 10 kilometers or more. And an individual particle will eventually start falling down. We'll call capital VT the terminal settling speed. What happens is that for a particle, there's a net weight force, a buoyancy force, and a drag force. The net weight, W minus B, must be balanced by the drag. But by Archimedes' principle, weight minus buoyancy is proportional to the density of the particle minus the density of the air times G. But this is typically negligible since rho air is very small compared to these particles. In the meantime, as we'll show later, the drag is proportional to mu Vt times some length scale of the body. We can equate these two to get terminal settling speed Vt. The particle will fall at speed Vt independent of the density of the air, even though the density of the air may increase by a factor of 10 or more as we go from high up in the atmosphere down to the ground. But density never appears in our equations, so Vt is fairly constant, independent of the density of the air. Meanwhile, viscosity changes with temperature, so Vt may vary somewhat with elevation, but if the temperature were constant this whole way, Vt would be constant. Our second observation is that time does not appear in the equations. The del UI del t term in our momentum or Navier-Stokes equation has also dropped out in our creeping flow approximation, and that's the only place time occurs. So, creeping flows are what we call quasi-steady. In other words, even if a flow is unsteady, the velocity and pressure fields depend only on the conditions at that instant of time. A corollary to this is that there are no history effects and no inertial effects.
Sir, didn't we see the same thing happen with potential flow?
Yes, Ned, good observation. The same thing happened in incompressible potential flow, because there too we lost time from our equation. Potential flow is also quasi-steady. For creeping flow, since Reynolds number is the ratio of inertial effects to viscous effects, when Reynolds number is very small, inertial effects are negligible. This is a very significant result. Consider swimming. As a human being, when we swim, we can push off of the wall, for example, and then glide. Without moving our arms or legs, we can still move in the water. This is an inertial effect. The Reynolds number for a person swimming is on the order of 10 to the 6th, which is a very high Reynolds number, and inertial effects are dominant. I calculated my Reynolds number as about 1.7 times 10 to the 6th, although every year my Reynolds number decreases as I age. Now consider a microorganism. Reynolds number is very small since microorganisms are an example of creeping flow. You may have a situation like this, where the tail, or flagellum, moves in an oscillatory fashion to propel the microorganism. But it turns out that microorganisms cannot glide. As soon as this flagellum stops oscillating, the microorganism immediately stops moving. There are no inertial effects. I show some video clips of this, in this case, sperm cells, and you notice that as soon as the sperm stops flagellating the tail, all motion stops. Some analogies include if you or I were trying to swim in honey or molasses. Since the viscosity is so large for these liquids, we would be trying to swim in creeping flow conditions. Another example is when you have thousands of balls in a pit and normally little children try to swim in it. They move only when their body is twisting and turning. Otherwise, everything stops. As in this short clip from the Big Bang Theory. Bazinga. Our third observation is that Stokes equations are linear. Nonlinear terms in our Navier-Stokes equation, such as u dot del u, have dropped out. These are the inertial terms. Because Stokes equations are linear, superposition of solutions is possible. As mentioned in a previous lesson, we showed that this applies to pressure, but it also applies to velocity. A direct result of this linearity is that creeping flow over a symmetric body must have a symmetric velocity field. Why? Because of superposition. We can write that if some velocity field u1 is a solution, then by the linearity argument, some constant times u1 is also a solution. If we let c equal -1, then negative u1 must also be a solution to our problem. Physically, if we have some symmetric body like a sphere at high Reynolds number, the flow is not symmetric. In fact, we'll get flow separation. Flow from right to left would look opposite. But at low Reynolds number, creeping flow, linearity tells us that flow from left to right is symmetric to flow from right to left. Mathematically, if this is our solution u1, this is our solution negative u1. Another way to write this is u1 of x equal u1 of negative x because of the left to right symmetry, assuming of course that x is at the center of the body. Keep in mind that this holds only for symmetric bodies. Finally, Stokes equations do not apply to 2D flow. This is a famous observation called Stokes Paradox. It follows directly because of our other observation that ρ does not appear in the equations. I explain this using dimensional analysis. Let's look at 3D flow first, specifically 3D creeping flow. Again, for some body of characteristic length L with some free stream speed, capital U, there will be a drag force on the body, made up of both pressure forces and viscous forces. With dimensional analysis, we list all the variables. Here, drag is a function of U, mu, and L, since there's no density in the flow. This is a review of your undergraduate dimensional analysis. We get D equal some constant times mu UL. This is our result of dimensional analysis for 3D creeping flow. Notice, by the way, that for any object of any shape, drag is a constant times mu UL, so drag is proportional directly to mu, and to U, and to L. The constant depends on the shape of the body. Now consider 2D creeping flow. Instead of a 3D object, we now have a 2D object where I'm trying to draw this into the page. Again, if we have some speed and some characteristic length, and if we take a slice or a plane through here, we can imagine a 2D velocity field. There will of course be a drag, but we'll call this drag sub 2D because d itself is infinite for a 2D flow, since the body extends to infinity into and out of the page. We define d2d as the drag per unit depth into the page, whereas this drag has dimensions of force. This 2D drag has dimensions of force per length, being force per a depth or a length into the page. Our dimensional analysis is similar to the 3D case, but when we go through the analysis, we find that d2d equal constant times mu u. The L has dropped out to make this drag a force per length. In other words, we're saying that d2d is independent of length scale L.
Well, that don't make no sense.
You're right, Dud. That doesn't make any sense. That would mean that the 2D drag on a small body would be the same as the 2D drag on a large body, or a body of any size, since L does not appear. Well, this is obviously false. What we conclude then is that inertial terms cannot be totally neglected in a 2D creeping flow analysis. Otherwise, we have Stokes Paradox. Another way to say this is that density must appear in the flow equations. We would have to add density in our dimensional analysis, and we have to account at least for part of the inertial terms in our flow equations. One proposed method of doing this is called Odens Improvement. What Odens did was include inertial effects, but a linearized approximation of the inertial terms. For 2D flow with some free stream velocity u, and we'll assume this is in the x direction. Stokes' equation was 0 equal negative del p del xi plus mu del squared ui del xk, where there are no inertial terms. Osane added back the inertial term rho ui del xi, but linearized as follows. His approximation in vector form is u vector is capital U, the free stream velocity in the x direction, where I can remove the I subscript, times unit vector I, plus u prime, which is also a vector. This is the free stream velocity, and this u prime is a perturbation velocity. What Osane did then was change this term to an approximate form, rho capital U del ui prime del x1. So Stokes' equation is improved to Osane's equation, which is rho u del ui prime del x1 is minus p del xi plus mu del squared ui prime del xk. This is Osane's equation, and you see that it has the same right-hand side as Stokes' equation, except we're now solving for a perturbation velocity, ui prime, and the inertial effects are approximated. The beauty of this equation is that it's still linear, but yet it accounts for some of the inertial effects. Odens Improvement gets rid of Stokes Paradox for 2D flows, but since it's linear, we can still use superposition. Of course, the algebra will be more complicated, but if you solve this equation, the 2D drag will increase as the body increases in size, as we expect. In other words, Stokes' paradox is eliminated.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.